I realize we've done a lot of review, and we're going to continue to do some review today and early next week. But again, looking at getting used to the language I use in describing stuff, and there are a couple of subtle little things about how things work at the very base level that I want to make sure you understand. And so today, we're talking about another one of those basic concepts, one that a lot of people don't like to work with. And of course, that is the fractions. Now, for this course, like I said, on test 1, there are about 14 problems, I believe 14 or 15 problems, where I want you to show your work, but you can use your calculator to double check it, or to do it as long as you can go back through and show all the carrying and common denominators and stuff like that. But when working with fractions, there is a fraction calculator out there. It does a great job, and as I had mentioned, it's the Texas Instruments TI-30. Usually it's the version 2, or I usually get the solar one just because the battery-powered ones do last a few years, but when the batteries go dead, it's like $6 or $7 for batteries and only $9 or $10 for the whole calculator. So I usually spend the extra $2 or $3 to get the solar. But anyway, we are going to go over how to do fractions without the calculator here. And we're going to start off. We had talked briefly on Monday about the two parts of the fractions. We know that that top number is a numerator. And the bottom number is a denominator. And we talked briefly about the meaning of those words. Numerator, to numerate, we talked about the census and going out and counting the population. That numerator is a count. Here we have 3 of something, just like having 3 inches or 3 cows or 3 pounds. The bottom number, the denominator, we have different denominations of money, of groups. Why are you not staying? My autosave is kicking in. Well, give me just a second here. Looks like I've got to do a restart. Give me just a second. My computer is going to have to reboot here. Some sort of a power error message. So anyway, we had mentioned that denominator is a name. That's just like inches or cows or pounds. It's a name. Here, that name is fourths. So one of the first things we will have to do is we'll have to discuss what does it mean for a fraction to have a name of fourths. Hopefully my computer restarts here quickly. Sorry about that. You may notice that a little bit different background. Fridays, this is my only class, so I actually teach from my home office on Fridays. Hopefully it's not too big of a mess for any of these classes. But it looks like we're coming back in. It doesn't look like there's too much damage. Okay, just have to get everything open back up, and then we're ready to go again. Okay, we should be popping back up here in a second. There it is. Screen's readjusted. There we go. Okay, so anyway, we need to know, what does it mean to have that name of a fourth? Well, the easiest way to illustrate this is to go back to that elementary school example or illustration of a pie or a pizza, or however you want to think about it. Pretend that looks like a circle. My artistic skills are very lacking. I'll warn you that up front in this class. To be a fourth means that we take that whole object and we cut it into 4 equal pieces. Pretend those are also equal. So we can look at it one of two ways. Either every whole object gets split into 4 equal pieces, or it takes 4 pieces to make up one whole object. Either way of thought works well for this. And then, of course, being 3/4, that means we have 3 of those pieces. Now, we had mentioned on Monday that when we add or subtract, we have to have the same name. And we saw examples where we had different names, in other words, different denominators. So one of the first things we need to be able to do is to rename these fractions in order to give them the same name. The simplest way with this illustration that we can do that is to cut them into smaller slices. Let's say, I'm just going to pick a number here. Let's do 3. I'm going to cut each slice of this pizza into 3 smaller slices. Again, pretend that these are all equal. That one's a little off, but not too terrible. So anyway, now instead of having 4 total slices, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total slices. Now that makes sense because we had 4. Each of them got cut into 3 smaller pieces, so 4 times 3 makes 12. What we actually have highlighted in yellow, we have 9 slices that we actually have. Again, we had 3 before. We cut each of them into 3 smaller slices. 3 times 3 makes 9. So the big question is, do we have any more or less pizza over here than we did before? No, it's exactly the same amount. 9/12 and 3/4 are exactly the same amount. They just look different. And the reason we were able to do that falls into this thing right here. Technically, that's a fraction in itself, 3/3. And what it's saying is, it takes 3 items to make a whole object, and we have 3 items. In other words, it equals 1. That is referred to as a unity fraction. And a unity fraction is any fraction where the numerator and denominator represent the same value. Now here they represent it in the same way. They're both just the number 3. But we can use unity fractions where we represent the same value in different ways. And we might have 12 inches and 1 foot, or 16 ounces and 1 pound. Same value, just represented in different ways. That would still be a unity fraction. So this worked because a unity fraction has a value of 1. So when we multiply or divide anything by 1, it keeps the same value. Here, I just picked the number 3 to multiply by. But normally, we have a set denominator that we want to go to, and we need to figure out what to multiply by. So let's say we need the denominator to be 35ths. We have to look at this and ask, what do we multiply 5 by to get 35? Of course, that's 7. And we multiply the numerator by the same amount, 7. Again, what we're really doing here is multiplying by 7/7, or 1. And of course, that comes out to be 14/35. 14/35 is the exact same value as 2/5. And on the other side, we need to be able to go the other way. 14/35. If I ask you to picture or imagine, it takes 35 objects to make a whole thing, and we have 14 of those pieces, it would be hard to do. Psychology tells us the human brain can picture on average between 7 and 13 items before things start to blur out on the edges. So picturing 14 items in itself is right on the edge, but having 35 items make a whole object is definitely outside the realm of human visualization. So it's easier if we can reduce that down to smaller, more numbers that are easier for your mind to work with. Well, here we multiplied both by 7. Over here we can divide both by the 7. 14 divided by 7 is 2. 35 divided by 7 is 5. And we've already established that 2/5 and 14/35 are the same value. Again, that's because we divided by that unity fraction, 7 over 7, which equals 1. We also could run into things like this, 44/7, where, again, it takes 7 items to make a whole object, and we have 44 of those pieces. That's too many pieces for us to visualize. So it would be simpler or easier for us if we could break that down into whole objects and then the pieces left over. If we tried to punch it in the calculator, of course, we could do 44 divided by 7, gives us something like 6.28571429 approximately. It tells us a little bit. It tells us that we can get 6 whole objects out of that, but it doesn't necessarily tell us the pieces that are left over. Typically, what we do with these is we actually do a long division and a remainder. 44 divided by 7, like this. 7 goes into 44 6 times. 6 times 7 is 42. We subtract, we have 2 left over. So what we end up with here, the 6 is our whole objects. So we have 6 whole objects. The 2 down here, the remainder, is our pieces that are left over. And of course, our denominator stays the same. It's still 7s. Obviously, you guys have done the conversion here between what we call improper fractions, 44 over 7, and the mixed numbers, the 6 and 2/7. Because they're called a mixed number because they mix whole numbers and fractions together. One example of going the other way, let's say we have 8 and 3/5, and I want to turn that from a mixed number back into an improper fraction. Well, I have to take this whole 8 whole objects and have to break it down into pieces. How do I know how many pieces? Well, the 5 here in the denominator tells me that each whole object is 5 pieces. So I take my 8 times 5 to get 40. The 8 whole object was 40 pieces. Well, I already had 3, so I have to add the 40 to the 3 to get 43 pieces. And of course, those are still fifths. Now, I realize all of you guys have done converting fractions, reducing fractions, renaming fractions. Not going to do any more than just the single examples here, but if you do need more examples, there are a few more in the video on Blackboard, or if you need more, let me know and I can post videos with more examples for you if that's something you struggle with. So let's get to 2/5 plus 1/3. This is an example we actually saw on Monday where they don't have the same name. They have different denominators, fifths and thirds. So we can't add them the way they're written. We have to find that I shouldn't say fabled, but that feared common denominator. Now, there are a lot of methods to find a common denominator. One of them is to just multiply the denominators. This will always give you a common denominator. Here, 5 times 3 is 15. That would be a common denominator for those two fractions. but it won't always give us something called the least common denominator. Least common denominator is the smallest common denominator. It's probably been stressed to you that you have to have least common denominator. It's not true. Any common denominator will work. It just takes a little more effort to do the problem if you have a larger denominator. The least one or the smallest one is generally simpler. There are a couple of methods to do this. One that we will look at later on in the course is factoring and using common factors. But for now, we can just look at lists. If I count up, I know that if I start with 5 times 1 is 5, 5 times 2 is 10, basically counting up by 5s. I have a pretty good idea what those are going to look like before I even start. We've done 5, 10, 15, 20. We've counted up by 5s a lot as we've practiced working with numbers. Then we do the other denominator, the 3. 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 3, and we keep working our way up, and we find that the smallest one that is in common is the 15. That is our least common denominator. So now when we go to work with our fractions here, or go to do the addition, I typically set them up vertically, just because my mind tends to work addition and subtraction vertically. I have 2/5 plus 1/3, and then I'm going to change them to that common denominator of 15ths. Well, to turn a 5 into a 15, I have to multiply by 3. Turn a 2 into a 15, or 2 also then has to be multiplied by 3 to give me 6. Multiplying that is that unity fraction, 3 over 3. Well, the second fraction is going to use a different unity fraction because I have to turn 3 into 15. That's multiplying by 5. So I multiply the numerator by 5 as well. 1 times 5 is 5. Again, 5 over 15 has exactly the same value as 1/3. Now that they have the common denominator, I can just go ahead and add. Remember, we combine the counts, we add the numerators, 6 and 5 make 11, and we keep the common denominator, the 15. Now, I'm not going to do any examples with simple fractions. Let's jump up to mixed numbers. We might have something like 7 and 1/6 plus 4 and 3/4. So we still need a common denominator. For 6 and 4, now notice I am also rewriting the whole number, the 7 and 4. For 6 and 4ths, we could just multiply 6 times 4 is 12, or 6 times 4 is 24, but there's a smaller one. We could use 12. So again, we're just working with a fraction. To turn 6 into 12, it's times 2. 1 times 2 is 2 12ths. Turn the 4 into 12, it's times 3, so 3 times 3 is 9 12ths. And now, just like we did with whole numbers on Wednesday, we start at the end of the number and we work our way backwards. So the fraction you can see is written at the end of the number, almost like it's just the last digit of the number, because that's actually exactly what it is. The fraction is just the last digit sitting at the end of the number. So 2 12ths plus 9 12ths, 2 plus 9 is 11, and we keep the name 12ths. Then we move over to the next digit. 7 plus 4 is 11. So 11 and 11 12ths. What if we had just multiplied the denominators to get the 24 as a common denominator? Well, 6 times 4 would be 24, so 1 times 4 would be 4. 4 times 6 would be 24, so 3 times 6 would be 18. When we add, we would have 22 24s. 4 and 7 and be 11 and 22 24s. And we would notice here, hopefully, that the 22 24ths can be reduced. Both the 22 and 24 can be reduced by 2, giving us 11 12ths. So 11 and 11 12ths. We get to the same result. We just had to do that extra step at the end of reducing our fraction portion. Not all of our additions with mixed numbers stay so simple. We might have 5 and 5/8 plus 3 and 4/5, let's go with. Our common denominator here is going to be 40. Again, some of you may have been taught just to rewrite the fraction. I always rewrite the whole number as well, so I don't forget about it. Turn the 8 into 40 was times 5, so 5 times 5 is 25. Turns 5 into 40, it's times 8, so 4 times 8 is 32. And now we can add. 25 plus 32 is 57. Pick the right number. 40. Now that is larger than 1. It's an improper fraction. So we'll go ahead and reduce that. 40 goes into 57 once with 17 left over. Now, just like with our whole numbers, we keep part of it and we carry part of it. We keep the 17/40ths and we carry the 1. 1, 5, and 3 makes 9. So we have 9 and 17/40ths. Subtraction works the same way, so I'm going to jump right into mixed numbers. We might have 9 and 2/3 minus 5 and 3/5. Our common denominator here is going to be 15 again. 3 times 5, so 2 times 5 makes 10/15. 5 times 3, so 3 times 3 makes 9/15. Just like with addition and just like with whole numbers, we start at the end and we work our way backwards. So we start with the fraction, which is our last digit first. 10/15 minus 9/15. 10 minus 9 is 1. We keep the 15ths. And 9 minus 5 is 4. Again, it doesn't stay that simple. We can run into things like 8 and 1/4 minus 2 and 5/6. So again, we need a common denominator for 4 and 6. We could multiply them and use 24, but there's a smaller one, which is the 12. 4 times 3 was 12, so 1 times 3 is 3. So 1/4 is equivalent to 3/12. 6 times 2 for 12, 5 times 2 is 10. Now, this is where it's very important that we do keep doing starting at the end and working our way backwards. So we do the fraction digit first. Because 3/12 minus 10/12 cannot be done. We're going to have to borrow. So we borrow from the ones digit, which is the 8. That'll become a 7. But we have to remember what we borrowed is one whole object. And that one whole object has pieces in it. And to know how many pieces it has, we look at the denominator. The denominator tells us there's 12 pieces. So we borrowed 12 pieces. So 3 plus 12 is 15/12. Note, 15/12 is equivalent to 1 and 3/12. The 3/12 is what was here before. The 1 is the part that we borrowed from the 8. Now we subtract. 15/12 minus 10/12 is 5/12. And 7 minus 2 is 5. Again, I'm not going to waste your time with a lot of examples there because I'm assuming you guys know how to add and subtract fractions and mixed numbers. Moving on to multiplication. So if we have 2/5 times 3/4. We said when we multiply, we don't need the same name. That means we do not need to find a common denominator. Next, we just combine the counts. In this case, that's multiplying the numerators. 2 times 3 is 6. And then we also combine the names. So that would be multiplying the denominators. 5 times 4 is 20. So we get 6/20. Now, if you're watching that closely, you might notice both of those can be reduced, can be divided by 2. 6 divided by 2 is 3. 20 divided by 2 is 10. So our result is 3/10. Some of you might be looking at that original problem right now, wondering, well, why didn't he cross-cancel? Others right now might be wondering, what's cross-canceling? Well, cross-canceling has a lot of different names. Some schools call it cross-multiplying, but there are other operations in math that are also called cross-multiplying, so I don't want to confuse them. What cross-canceling is it looks at these fractions and it realizes that in our result, the numerator is just going to be 2 times 3, and the denominator is going to be 5 times 4. And we see that the 2 and the 4 can both be divided by 2. So we do that before we multiply. 2 divided by 2 is 1. 4 divided by 2 is 2. Now when we multiply, 1 times 3 is 3, and times 2 is 10. We've reduced our answer before we multiply. Now in this problem like this, it really doesn't make much difference whether we cross-cancel to reduce first, or if we multiply it out and reduce at the end. But we will run into examples like 24/25 times 35/36, where it's a lot more work if we don't cross-cancel. So if we just want to go in and multiply here, 24 times 35, what is that? 840, I believe. And 25 times 36 is 900. Some of you might look at that and realize both of them can divide by 60. I didn't at first, so don't worry if you didn't. But I do notice they both end in 0. So we can divide by 10. 840 divided by 10 is 84. 900 divided by 10 is 90. Now we can see they can both be divided by 2. 84 divided by 2 is 42. 90 divided by 2 is 45. And they can't be divided by 2 anymore because the 45 is odd. 45 can be divided by 5, but of course 42 doesn't end in a 0 or 5, so we can't divide by 5. They can both be divided by 32, or by 3. There's a little trick there. If you add the digits, 4 plus 2 is 6. That's divisible by 3, so 42 is divisible by 3. 4 plus 5 is 9. That's divisible by 3, so 45 is also divisible by 3. So 42 divided by 3 is 14. 45 divided by 3 is 15. So 24/25 times 35/36 is 14/15. We got there, but we worked with some big numbers and had quite a few steps. If we had started off cross-canceling, it would have saved us a bit of work. We'd have looked at this and said, okay, 24 and 36 can both be divided by 12. 24 divided by 12 is 2. 36 divided by 12 is 3. And 25 and 35 can both be divided by 5. 25 divided by 5 is 5. 35 divided by 5 is 7. So now we have 2 times 7 is 14. And 5 times 3 is 15. That seems like a lot less work to me. But some people do struggle with the cross-canceling. So you will, if you do things correctly, always get the correct answer, just multiplying it out and reducing it. The cross-canceling comes in really handy when we get into algebraic variables. We don't do a lot of algebraic variables in this class, but if you're going on to a college algebra or a course like that, you would have to do reduction with algebraic fractions. The cross-canceling is way easier if you have variables and powers involved. So let's jump up to mixed numbers for our multiplication again. Let's do something like 5 1/3 times 2 4/7. Now, multiplying mixed numbers is actually a pretty difficult process. In fact, if you went to any university and found 10 math majors, I would actually be surprised if even 1 out of the 10 could show you how to multiply mixed numbers correctly. So you might be wondering, well, pretty sure we've multiplied them before. Well, what we have usually done is we take a shortcut. We convert those mixed numbers into improper fractions. 5 times 3 is 15, plus 1 is 16/3, times 2 times 7 is 14, plus 4 is 18/7. Now, this is multiplication in every way. We can cross-cancel here. 3 and 18 both divide by 3. 3 divided by 3 is 1. 18 divided by 3 is 6. Then we multiply. 16 times 6 is 96. 1 times 7 is 7. And then we do have to reduce this back to a mixed number. So 96 divided by 7. 7 goes into 9 once. Subtract 7, that's 2 left over. Bring down the 6. 7 goes into 26 3 times. 3 times 7 is 21. There's 5 left over. So that is 13 with 5 of those 7ths left over. That wasn't so bad. But just because this is a little bit of a higher level course for you, let's go back and look at the process for actually multiplying the mixed numbers. Now, to let you off the hook, you don't have to write this down. I will never ask you to repeat this, but I just want to show you so that you see that there actually is a process to do it. So if I have 5 1/3 times 2 4/7. When we're multiplying whole numbers, if I have something like 43 times 28, the 8 here has to multiply the 3, but it also has to multiply the 4. Well, the same type of thing happens here with the mixed numbers. The 4/7 multiplies the 1/3, but it's also going to have to multiply the 5. So we'll start out with 4/7 times 1/3. 4 times 1 is 4. 7 times 3 is 21. So it's 4 21st. 4 over 21. 4/7 times 5. Well, to multiply a fraction by a whole number, we just make the whole number into a fraction by putting it over 1. That's 5 over 1. 4 times 5 is 20. 7 times 1 is 7. That is 2 6/7. Now we do the 2 times 1/3. So again, we make that a fraction by putting it 2 over 1. Times 1 over 3, that's just 2/3. And finally, the 2 times 5 gives us 10. But we still need to combine these. To do that, we need common denominator. That common denominator is going to be 21. So this will stay 4 21st. 7 times 3, so this will be 18. 2 and 18 21st. 3 times 7, so 2 times 7 will be 14 21st. And then just our whole number of 10. So now we go ahead and add. 7 and 18 is 22, plus 14 is 36. 21st. We reduce, 36 21st is 1 and 15 21st. That can actually be reduced. Both 15 and 21 can be divided by 3 to give me 5/7. So we keep the 5/7 and we carry the 1. 1 and 2 makes 3 plus 10 is 13. Notice we got the same answer. This is a lot more work. I'll never ask you to repeat that, but I wanted to show you that it is possible that the converting into mixed numbers and multiplying is a shortcut. Okay, so the last thing I want to show you today is dividing fractions. And dividing fractions is always a little bit of a surprise to students because what we were taught, just like with the dividing whole numbers and that whole repeated subtraction thing, what we were taught for dividing fractions is, again, a severe shortcut or abbreviation of the full process. If I have something like 12 25ths divided by 4/5, we said that division follows the same rules as multiplication. Well, when we multiply, we just multiplied straight across. Numerator times numerator, denominator times denominator. So when we divide, can I do 12 divided by 4 is 3, 25 divided by 5 is 5? Does that work? Is that the correct answer? It actually is. Does that work every time? Actually does. So why don't we do it? Well, the reason we don't do it is because we run into things like this. 3/4 divided by 2/3. If I tried to divide that out, 3 divided by 2 is like 1.5, and 4 divided by 3 is 1.3333333, repeating. It doesn't divide out nicely. Well, what we've been taught to do is to change it. We keep the 3/4. Just like when we worked with integers, the operation works on the number that comes after it. So the division operates on the 2/3. So instead of dividing by 2/3, we were taught to multiply by something called the reciprocal, which is just flipping it over, 3/2. And now we have 3 times 3 is 9, 4 times 2 is 8, 9/8, or 1 1/8. So the question is, where did this multiplying by the reciprocal come from? It actually came from this process up here. If I started out with 3/4 divided by 2/3, the actual real division of fractions involved this extra little step here that we usually skip, and that is we look at the number, the fraction we're dividing by, and we make sure it can't be reduced anymore. Here it cannot be reduced anymore. So now we're going to take the numerator times the denominator. 2 times 3 is 6. That 6 is our key to renaming the first fraction so that we can divide. So now we take that first fraction, 3/4, and we're going to rename it using the 6. So we're going to multiply by 6/6. 3 times 6 is 18. 4 times 6 is 24. Now we'll go ahead and divide by the 2/3. Now the 18/24 here is the same value as the 3/4. We've just changed its appearance. So this is still 3/4 divided by 2/3. 18 divided by 2 is 9. 24 divided by 3 is 8. 9/8, or 1 1/8. Exactly what we got over here. So how did we get from this mess, which looks really ugly, to something as simple as multiplying by the reciprocal? Well, it's not as big of a logical leap as you might think. Somebody looked at this problem here at one point and realized, hey, we have 3/4 times 6/6, and then divided by 2/3. And what they noticed is if we fudge our order of operations just a little bit, there are some circumstances where we can get away with doing things if the operations happen in a certain order that we can alter our order of operations. And here, what they did is they said, let's take this 6/6 and let's divide by the 2/3 first. And what they noticed, 6 divided by 2 is 3. 6 divided by 3 is 2. They noticed that what they got here was always this fraction flipped over. So they just named that the reciprocal. And then all that was left was to take the 3/4 times that, giving us, of course, the 9/8, or 1 1/8. So this process here of multiplying by a reciprocal is just this whole process that we saw here, just skipping a whole bunch of steps and jumping right into multiplying by that reciprocal. Again, let's jump up to some mixed numbers. I have 5 1/3 divided by 1 2/5. Just like with multiplying, we're not going to divide with mixed numbers. We're running a little short on time, so I won't show you the long process there, but there is one. It's just not very pretty. So let's change these into improper fractions. 5 times 3 is 15 plus 1 is 16/3. Divided by, we're still at division here. 1 times 5 is 5 plus 2 is 7/5. We still need to change it to multiplying by the reciprocal. So the first fraction never changes. That's 16/3. Remember, the division operates on the fraction coming after it. So that's going to be times, the reciprocal will be 5/7. Now, this is multiplication in every way. If something could cross-cancel, we could go ahead and cross-cancel it here. In this case, nothing does cross-cancel. So we'll do 16 times 5 is 80. 3 times 7 is 21. Now we do still have to reduce this into a mixed number. So 21 goes into 80 3 times. 3 times 21 is 63. We subtract, we have 17 left over. So this is 3 17/21. when we're dealing with fractions, I mentioned that unity fraction earlier on. A unity fraction, we had, like 3 over 3 or 6 over 6. Those are the unity fractions we use because right now we're just dealing with numerical fractions. But when we start throwing in measurements and units and stuff like that, those unity fractions could have other things in it. Any two things that are equal can be used to create a unity fraction. We know that 1 foot equals 12 inches. That can become a unity fraction. So if I have 4 feet and I want to convert it, I can actually use that unity fraction. First, I have to make the 4 feet into a fraction by putting it over 1. And now I know that if I multiply by a fraction that has one of these as the numerator and the other as the denominator, that I might change the appearance, but I can't change the value. So since there's feet here, I'm going to put feet down here because I want them to cross cancel like we were reducing our fractions. So I'll put 12 inches here. Now again, since 12 inches equals 1 foot, this has a value of 1. So multiplying by this will not change the value of our original fraction. So the feet do cancel out. 4 times 12 inches is 48 inches. And on bottom, we double check 1 times 1 is 1. So 48 inches over 1 is just 48 inches. We use that to make our conversion. Now, many of you have done measurement conversions enough that you don't need to go through the unity fraction to convert feet into inches. But this is medical math, so we might run into a situation where we have a medication that is dissolved in fluid, where it is dissolved with 25 milligrams of medication in 8 milliliters of solution. So if you're told that that patient needs 150 milligrams of medication, to figure out how much of that solution to give to them, we put it over 1 to make it a fraction. And we're going to multiply by a unity fraction, a conversion factor, basically. And in that unity fraction, we know 25 milligrams is equivalent to 8 milliliters of solution. So we put milligrams on bottom so they cancel with this. So it's 25 milligrams. So the 8 milliliters goes on top. This again, oops, did not mean to keep that as red. This is a unity fraction. 8 milliliters and 25 milligrams is equivalent, so that is equal to 1. So multiplying by that will change the appearance of this fraction, but not the value. So the milligrams cancel out. 150 times 8 milliliters is 1,200 milliliters. On bottom, 1 times 25 is 25. We go ahead and reduce that. 1,200 milliliters divided by 25 is going to be 48 milliliters. So in order, with this solution concentration, in order to get the patient 25 milligrams of medication, we have to give them 48 milliliters of solution. Or sorry, not 25, 150 milligrams of medication. We have to give them the 48 milliliters of solution. So just wanted to show you briefly here at the end that there are uses to these fractions beyond the basic calculations. This is what we're going to be doing in units 2 and 3 of the course, is dealing a lot with the process here is called dimensional analysis. And it really is the easiest way to deal with medical conversions. Okay, so for now, let me get you out of here. Page 18 through 21, 1 through 97, the odds. Now again, I realize that you guys have worked with fractions. You can do the basic operations. If you're good with fractions, I'm not going to ask you to waste your time on the first, basic practices and calculations. But make sure you do at least some of the word problems so that you're familiar with it. And make sure you do enough of the calculation so that when the test hits here in a couple weeks, you are able to show the steps, show converting the mixed number into an improper fraction so you can multiply, show the carrying and borrowing and common denominators and all of that. And so with that, you all have a great weekend. and we'll see you hopefully all on Monday. Bye.